Okay, so let me do this question. If you've been looking ahead at the homework help videos, I have done this question before, but that was some years ago in an in-person classroom setting, so the board wasn't really readable. It's been on my list to do again for a while. Now it's finally its turn to be done. So let me just to doodle a little bit as I'm reading the question. So it says there's an object of some height. And let me just use letters for that. This is height h, O. That's our standard letter for height of an object in an optical system. Some distance. Let me call this a DO because it feels like it's going to become our object distance. So, and then it says a diverging lens of some focal length. So let me draw a diverging lens. And with some let's see, it's more than focal length away, so let me draw focal length. This is just for rough scale. It doesn't have to be super accurate. I do like to be within just the general correctness. Oh, some focal length, and then behind the diverging lens, there's a converging lens of focal length. Distances are very small. So I need to place a converging lens. Let me do it in different color for variety. It looks like it's the same magnitude of focal length for this converging lens. So, all right, it says in the next few steps, you will find the location and size of the image. So the question, it looks like it's going to be asking where's the intermediate image and all that. Let me just do a kind of rough sketch of ray tracing so that I have some idea of where things will be. So that if for some reason, as I go through the rest of the steps, if I get something unreasonable, it'll be easier for me to spot, having kind of seen conceptually what things should look like. So the ray tracing refers to drawing of two principal rays. I know there's a third one that sometimes gets brought in. Two is all you need. The third one is really unnecessary, and especially when you're doing it by hand, it could actually cause confusion. So you got two rays. One that's going to be incident parallel to the lens. Oh, sorry. Incident on the lens parallel to the axis. That's the principal ray number one. That ray bends in a way that's related to the focal length. So if this had been a converging lens, it would bend towards the optical axis so that it goes through the focal point. If it's a diverging lens, then it bends away in such a way that it looks like it's coming from the focal point on the incident side. So this is my principal ray number one. And then the second principal ray, it goes through the middle of the lens and it doesn't do anything. It just goes straight through, like it's a glass pane that it's going through. So that's the second principal ray. Let me just, I drew it a little bit too far past the second lens. Let me not do that. I try to only draw the real rays as a solid lines and any kind of projected virtual rays as a dotted line. So I could, have this that from here on dotted, because then it'll be affected by the second lens. Now, in the way we analyze it, the first lens will form an image. It looks like it should be forming an image here. And I realized that the accuracy of my drawing won't quite tell me if this image will be, which side of this focal point it'll be. If it's farther away, then my final image really should be a real image. If it's, where it appears to be like inside the focal point, then my final image will be a virtual image. So that's a kind of uncertainty that I have. Let me, so this is a real object because everything to the left of this second lens is the incident side, and everything to the right of the second lens is the outgoing side. When the object is on the incident side, that's a real object. So this is a real object. So I can do the ray tracing like I do it for a real object. So I'm going to, let's use green. So I'm going to do first the principal ray. That's the ray that's incident, that's traveling parallel to the axis, incident on the lens. Then it'll bend in a way that it goes through the focal point on the outgoing side. It's a converging lens. And then it'll keep going. And the second principal ray will go through the middle of the lens. And when it does, so in this particular setup, these rays should look almost parallel. That's because where this real object is. And we'll go through the rest of the questions to see if we should expect real final image or virtual final image. So the first question, part A, asks, where is the intermediate image formed by the first diverging lens? So I do the ray tracing just so that I have a sense of where things will be. But in terms of getting the actual answers, your number one tool is going to be the lens equation. The one that says 1 over object distance plus 1 over image distance is equal to 1 over focal length. And here, focal length, when I plug in, I'll plug in minus 16 centimeters. We usually don't indicate the sign within the equations. We just let our value, the variable values take on positive and negative value according to the sign convention. So, to find the DI, you need to do some algebra, solve this for DI. In the interest of time, this is a long question. Let me do this in my head. You can verify for yourself that I didn't make a mistake. DI should be F times DO divided by, I think, DO minus F. Now, I said doing it in my head, I lied. This is more of a memorized value. So let me actually do it in my head. Yeah, I think that's right. Yeah. This comes up so often that I have it memorized. And even though the semester's new, it's been a year since I've done optics, I still have this memorized. Now, if you want to do the algebra by hand, then what you have to do is move the 1 over DO over, combine the fraction, then, a denominator will be this F times DO, numerator will be this, and then you take the reciprocal to get this expression. So I think I can just plug in the numbers. Let's see, are the numbers something I can do in my head? 16, yeah, I don't think I want to do that in my head. Let me just use calculator. So, using a calculator, F, I'm going to be careful with the signs and plug in the number of minus 16. That's my focal length. Centimeters times the object distance, 28 centimeters, divided by, parenthesis, 28 centimeters minus, and this I have to be careful, negative sign 16. That's the, 16 negative sign, yeah. 28 minus, and then minus 16. So it'll actually effectively be 28 plus 16. So, all of that is equal to minus, good, we are getting virtual image. And the distance-wise, it looks like it's going to end up inside the focal length. So we'll be forming a virtual final image. So, let's say our answer here is minus 10.2 centimeters. And you can work out the unit. You have centimeter squared on the numerator, centimeter on the denominator. You end up with a centimeter. Good. Should I verify? Let's just double check to make sure. I'm a little rusty, coming back to optics. Let's just make sure I didn't make any mistakes. So 10.2, minus 10.2. Yeah, sign which side the image is on. These are the reminder of our sign convention. Okay, so part D. Where is the final image formed by the second image, second converging lens? So this is really what the sketch was for. So one potential mistake that somebody could make that you should definitely avoid is, trying to use this as it is somehow some sort of DO2. Like, don't do that. That just doesn't work. So what you have to do is you have to place the image in your setup. So what this result is telling you is that where image is, that's going to be distance of 10.2 centimeter on the opposite to the outgoing side of the lens. So, on this side. So you are given some of the lengths here. You are given the distance between the lenses, 4 centimeters. Here, 4 centimeters. So you could actually do the math here and figure out. So from the converging lens to the diverging lens is 4 centimeter. From diverging lens to where the image is, which will now be treated as object, is 10.2 centimeter. So the second object distance should be 14.2 centimeter. And that's the number I'll be using. And it's a positive number because, again, this is a real object that's on the same side as the incident side of the lens. So with all that, let's do the algebra again. It's the exact same thing. It's the exact same equation, 1 over dO plus 1 over di, with this 2 implied, I'm just too lazy to write it down, is equal to 1 over f. And if you don't want to make sure that you don't confuse the stuff, this is f1, this is f2, this is plus 16 centimeters. Again, doing the algebra in my head, by which I'm just copying that memorized formula that I had on the board from before. So dO minus f2. And now I just plug in the numbers to get what it is. So the focal length this time is, let's just have the calculator come back. So focal length this time is plus 16 centimeters times the object distance we worked out before, 14.2, divided by the object distance, 14.2 minus 16. This is where I see, you're going to get a negative denominator. So when you finish the calculation, you're going to have a negative image distance, minus 126 centimeter. And so it's too far away for me to try to draw it. That's why really these two rays will appear approximately parallel, because this is kind of close to the focal point. So that's where the image is now. Yeah. So, and the question is still asking for image distance from second lens. So we can give this, and the minus sign indicates the virtual image that's on the opposite side of the outgoing rays. We'll plug in all the numbers together at the same time. So let's move on to C, which asks, how large is the intermediate image formed by the first diverging lens? So intermediate image height is, and then use the sign to indicate whether the image is upright or inverted. So we do have some sense from our previous drawings that this image is going to be upright. So hopefully we get a positive magnification factor. And the magnification, in terms of how it's defined, it's the linear magnification is defined as the image size divided by the object size. And in fact, this is what you use to solve for your image size. Now, if this is the only relationship you had and it's all circular, you can solve for it. There's a formula that's been derived in the lecture that relates these relationships in terms of these distances that was already in your question. And you can look up the derivation. When you do, it'll be minus image distance divided by the object distance. So a good geometric argument. I do encourage you to take a look at it. In the end, you're kind of using this formula, which could have been memorized. That's fine. So how large is intermediate image? Let's solve this for HI. Again, doing the algebra in my head in the interest of time. HI is equal to minus of, let's see, di divided by do times ho. So this factor is really the main thing you need, and then you just, it's a proportionality factor. You multiply to the object size to get the image size. So if your image distance and object distance are both real, that actually results in an inverted image. Here we will result in an upright image because our image distance was negative. So when I do the calculation, I'm just going to say it's all going to be positive because two minus cancel out. So I have plus 10.2 divided by the object distance. I placed it how far away? 28 centimeters. So I think that makes the image smaller. Yeah, 0.36, that's the fraction. And then I multiply by object height, 2.6 centimeter. To get the actual image size, 0.947. Yeah, that is a small. 0.947 centimeters. Hopefully that's all correct. And the positive sign here means it's upright, which matches with the ray diagram that we've drawn, just to get a sense of what the question looks like. So that's the intermediate image. The last question now asks for how large is the final image. Then you do the same thing. The only thing that's really changing is you're doing it with the second stage. So magnification of the second stage is, again, the height of the second stage, height of the object for the second stage, which actually is this. This is, your image from the first stage is your object for the second stage. So let me actually write it that way. Let's write this as HI, which is that number there. So that's equal to minus di over do. And image distance being negative, I think this is going to end up being positive again. So let's solve for the final image height. So hi2 is equal to minus di. If this is beginning to feel repetitive, that's great. Exactly what I'm going for. The lens problem solving, it's almost like a standard strategy we were teaching in Physics 4a, except right now we are not giving you a specific set of steps, but it's a standard enough question where once you are used to doing this type of question, it should be almost automatic. Not saying that's the goal, but these are not hard questions. Sometimes it can be a really tedious question. Like this is only 2 stages. Imagine you had 3 stages. It can be really tedious. So, okay. Minus, and then minus 126, so plus 126, divided by the object distance. I worked it out before. I worked it out above. That's why I write things down. 14.2 centimeters. So that's the ratio there. Times, we had the image, this distance, which is 0.947. Again, that's why I write things down. So that's equal to 8 point, that now it's large, 8.403. And I believe it was a positive image size, which indicates that the final image is also upright. And I think this might be some kind of a telescope setup, or at least it's very similar to a telescope setup. So let's plug in all these numbers, make sure that I didn't make any mistakes. Just gonna dock this. Oops. Yeah, I can leave it there. I usually keep it over here, but it's fine. I moved the dot for other reasons. So minus 126 centimeters plus 0.947 centimeters plus 8.403 centimeters. So that's the problem for 2 lens setup. Again, it's not difficult. It's just can be, it's got multiple steps. So hopefully you feel comfortable with the multi-step problem solving, which is the main thing we teach in all our physics classes. And each of the steps that's involved there is fairly simple algebra. Some attention to the sign convention needed. And just keep neat, organized the work, and you should be done relatively quickly. Oh, and in this class, we won't ever ask you like 3, 4 lens setup. I think once you know how to do 2 lens setup, you can do multi-lens setup. It's just a matter of time. So I won't ever ask you 3 or 4 lens setup questions. Although a lot of the practical optical devices are designed with the multiple lenses.